When I start teaching the concept of pi in geometry, I start with a square. That might seem odd, but it's important to get the general idea for what pi is about, probably even more so than knowing an exact value for pi. Alright, so here's the idea. This little dotted line here, I'm going to call, just for convenience, I'm going to call this the diameter of this square. It's the distance across the square. Alright, it's the same, turns out, as the side length. But for a circle, we talk about going straight across the center, so I'll do the same thing for a square. Alright, so here, if I start with a square that's 1 centimeter across, then the side length is 1 centimeter, and the distance around it is 4 centimeters. Okay, pretty clear. The ratio of the perimeter to the diameter is you take the distance around divided by the distance across, and 4 divided by 1 is 4. Let's go to a 2 by 2 square. Here it's 2 centimeters across, it's 2, 4, 6, 8 centimeters around. Notice if I take the ratio again of 8 to 2, I come up with 4. Okay, so what I'm getting is the same ratio. Look at this number right here, and notice that as I change the side, the diameter changes, the perimeter changes, but the ratio of the perimeter to the diameter stays constant. And so the magic number for squares is 4. Okay, and notice that it stays 4 no matter what size I make the square. Okay, let's now add a circle. If I trace a circle inside the square, it's like I'm going around the square, but I'm cutting off the corners. So I'm going a shorter distance than I would for the square. So the distance, this ratio, which is 4 for the square, must be something smaller for a circle. In other words, if I take the distance across the circle, if I multiply by 4, I would get the distance around the square. I have to multiply by something less than 4 to get the distance around the circle. Okay? Let's go to a hexagon. A hexagon is a 6-sided figure, and a regular hexagon is made up of 6 equilateral triangles. So all 3 sides of these triangles are equal, and if you pile 6 of these together like this, you'll have a regular hexagon. Okay, so if I take an edge length here of 1, let's go down here. If I let the edge length be 1, the distance across the center is 2. So like the diameter, if we could think of it that way, across here is 2 for this hexagon. But notice that the distance around is 6. Okay, so this is, if this is 6 around and 2 across, the ratio of 6 divided by 2 is 3. Let's go to a larger hexagon. This time it's, the side length is 2, the diameter is 4, and it's 2, 4, 6, 8, 10, 12. So the distance around is 12, the diameter is 4, and if I take 12 divided by 4, I get 3. So the ratio of the perimeter to the diameter, again, stays constant. Notice how this number stays constant, even though these numbers are changing. So whatever size I have, the magic number for hexagons is 3, regular hexagons. Let's put a circle around a hexagon. And notice that the distance around a circle that has the same diameter as this distance across the hexagon has to be something greater than 3, because if you were to walk around the circle, you'd be going farther than if you walked around the straight segments here to make up the hexagon. So now we have a square, which is sort of an outer limit, and a hexagon, which we have seen as an inner limit. Notice that for this distance across, straight across the center, if we put a circle that has that same diameter, it's going to be something greater than the hexagon, something less than the square. Therefore, the magic number for circles, and the magic number means the distance around compared to the distance across. The ratio of the distance around to the distance across. The circumference, we call it for the circle. We call it perimeters for non-circular shapes. But whether you call it perimeter or circumference, it's just a vocabulary thing. But the perimeter, so to speak, of the circle is some number between 3 and 4 times as big as the diameter. Okay? So that's where pi comes from. It's the idea that for every circle, regardless of size, the ratio of the distance around compared to the distance across is always the same. And we've shown that it's a number between 3 and 4. Now, using simply a hexagon and a square, we can't go much beyond this. We have the first digit of pi is 3 point something. In order to get a more accurate version of pi, we can start with the hexagon, it turns out. And if we follow the method that Archimedes used thousands of years ago, we're able to get a number that's a very accurate representation for all practical purposes of pi.